campus. And, he's my very good friend. I'm so happy, Alain, to have you here with us. I mean, virtually, but still, I feel like you are there with us. And just to say a little bit about his accomplishments, I mean, he is a very well-known figure in the world mathematics as far as this, this Diophantine equations, these Fibonacci numbers, Diophantine tuples, as we are having. We have seen in the lecture of Professor Andres Duela that there do not exist 5 tuples as far as these integers are concerned. That's the result which recently Alain has proved with his collaborators. And he has, he's a very prolific researcher and more than 150 publications that I see, and has almost worked with who's and who of number theory. And so it's a great pleasure, Alain. And so today the title of his talk is Coincidence between K Fibonacci numbers and Product of 2 Fermat numbers. Professor Alain Togbe.
Yes, good morning again. It is morning here. It is 7:30. It is nice to see you again, Professor Chakraborty. And also my friend Azizul, and thank you for the invitation. Thank you for all the organizers for this nice conference. And since 3 days I'm following as I can because of different of time, but it is a very nice conference, and I'm very happy to be here. And also I would like to honor my friend Michel at the end of the talk, because I won't be online the entire seance presentation of tomorrow. So I would like to give a special thank to Michel at the end of my talk. So my talk, it is about, like you have seen, coincidence between K Fibonacci numbers and the product of 2 Fermat numbers. For my talk, I will give a motivation of this topic, and I will also state the first result that we obtained, and I will give a kind of proof, a very small sketch of the proof, and also I will give us other results that we obtained, and I will think about other generalization of sequences. And at the end, as I said, I will discuss about Michel a little, how we work together. So that is the outline of my talk. By the way, this work is done jointly with 2 of my students, one former student, he's a doctor now, that is Salah Rian, he's from Algeria. And the second, it is a student from Senegal, and his name is Alain Gay. Okay, so let me refresh the memory for some young scholars here about some sequences. And we know very well the famous sequence that is the Fibonacci. It is defined by these first terms, f0 equal to 0, f1 equal to 1, and we have the recurrence here. The second thing we can say about Fibonacci numbers, it is about the roots, the principal roots of the characteristic equation of the sequence, that is the s squared minus x minus 1 equal to 0.
Alain, just a second, maybe your slide is not moving. Just try once more.
Oh, okay, let me try one more time.
Just share once more.
Okay.
So just to say hi to Francesco, I can see Francesco is there. So
yes,
hi. And next to Michelle, that's it.
Yes. Could you see it is moving now?
Yes. Yes, it's fine now, Alain.
Okay.
Please go ahead.
Francesco, I'm happy to see you.
Yeah, we are all happy to see you, Francesco.
Yes. So anyway, the binate formula for the Fibonacci number for a Fibonacci number is given by this expression here, where we use the dominant root alpha and the second root beta. Another sequence we can talk about, it is related to Fibonacci number, Fibonacci sequence, it is the Lucas sequence. And we have the initial terms 2 and 1, and the relation is the same. And they have the same characteristic polynomial, characteristic equation, and same roots, but the binate formula is given by this expression here. Another sequence we can talk about, it is the Pell sequence. The Pell sequence is defined by the initial terms 0, 1, and then we have the relation, the recurrent relation here. And similarly, the characteristic equation is s squared minus 2x minus 1 equal to 0, and the roots are given by 1 plus square root of 2 and 1 minus square root of 2. Similarly, the binate formula is given by this expression here. For any m greater or equal to 0, I can put n greater or equal to 0. There is a typo there. Now, before I will continue, sometime, let's say 30 years ago, it was very hard to work with these sequences. And it was a little difficult. People were thinking that it is difficult to study the properties of these sequences. And suddenly we have a very nice result when Kohn tried to look at all the powers in the Pell sequence. And he arrived to the result that only the initial terms are powers of a number for k greater than 2. In the same direction, Bugeaud, Mignot, and Sisek in 2006, they tried to look at what happened with Fibonacci and Lucas sequences. So they consider first the Fibonacci sequence, and they realized that the only powers in the sequence, are 0, 1, 1, 8, and 144. I will tell you that the method is not straightforward. They use a combination of Baker's method and modular method to obtain the answer. It is a big paper, and that changed a lot the idea about the sequences. So similarly, they look at the Lucas sequence, and they realize that the only powers we can have are 1 and 4. Okay. So we can think about a generalization of a Fibonacci sequence. So in fact, it is we have a nice one. We have many generalization, by the way. And the one we consider here is defined by the initial terms, only zeros, and then for f1k equal to 1, for k greater or equal to 2, and the recurrent sequence or relation is given by this expression here. So the idea is to look if we can have the result obtained by Bugeaud and his team, or by Kohn, or if we can have other properties or other results related to generalized Fibonacci sequence. So in fact, we can see that if we look at the generalized sequence, for k equal to 2, we have a Fibonacci sequence. K equal to 3, we have a Fibonacci sequence, and so on. Okay. So Bravo and Luca in 2012, they tried to see powers of 2 in the generalized Fibonacci sequence. And they come to the fact that the only power we can have, it is when k equal to 2 and n equal to 6, that is exactly 8, that is 2 cubed. So it is a very nice result. And after that, people try to look at all the results. It is like here, we are going to define what we call Fermat numbers. A Fermat number is a number of the form 2 exponent 2n plus 1. So if we look at the first terms of the Fermat numbers sequence, we can have 3, 5, 17, 257, and so on. So there is a classification of sequences that we know, and that is the number of these sequence in the classification. So Fermat's numbers, they have some properties, very nice properties. Like every odd prime number of the form 2 exponent k plus 1, it is a Fermat number called Fermat prime. Another thing that we can notice, and if you don't mind, I will come back to the list I have here. We can see 3, 5, 17, 257, 65,537. So these numbers are primes. And there is a conjecture that the only first 5 prime Fermat's numbers are prime. So we can see that these numbers are here. This conjecture is still open. So young researchers, they can attack that and try to solve it. Now, related to that, we have some results related to Fermat's number. If we consider, for example, Padovan's sequence, that is defined by this relation here, with the initial condition, P0, P1, P2 equal to 1, and we can see that the result is that the only Fermat numbers in the Padovan sequence are given by 3 and 5 that I put in red here. So this was obtained by my 2 former students, Sheffield and Salah. In the same direction, because there is another sequence related to the Padovan sequence, it is the parent sequence, we can see that in the same direction, we can see that the only Fermat numbers in parents sequence are given by 0, n equal to 0, 3, 5, 6, and 10. So that is the number that I put in red here. Okay, now how we can say about Fermat's numbers and the generalized sequence, Fibonacci sequence I talk about. There is the one result obtained by Bravo and Herrera. And they prove that the only non-trivial solution of the Diophantine equation Fnk equal to 2m plus 1, it is the only solution are the solution given here. So we mean that we have Fibonacci, only Fibonacci numbers, and we have F2, F4, that is equal to 1, that is equal to 2 exponent 1 plus 1, it is 3. And we have F5 also, and it is the case m equal to 2. So we can see that there is exactly one Fermat number in this set, because this it is not a general form of Fermat numbers. So we can see that. So exactly 3, exactly 2, that is F4 and F5. So this give us the motivation of the first paper we obtained. We ask ourselves, instead of having only one Fermat number, we can look for a product of 2 Fermat numbers. Another idea can be somebody can look the sum of 2 Fermat numbers. So it is not solved. So it is an open problem that somebody can look at that. So what we have done is that we prove that if we consider this equation here, we have exactly 2 solutions given by F6, 4. So we mean that n equal to 6 and k equal to 4. And we have the product here, 2 exponent 1 plus 1 and 2 squared plus 1 and F9, 3. So n equal to 9, k equal to 3, and we have a perfect power here. So from our 2 solutions, we can conclude that only F6, 4, that is 15, is the product of 2 Fermat numbers. Okay, the next step I will do will be to give a sketch of the proof. And to do that, I need to remind a few properties of the generalized Fibonacci sequence. In fact, the characteristic polynomial is given by the irreducible polynomial over Q. And there is only one real root that we will call alpha k here, but only real roots, that is alpha k. And the it is the unit circle. The other roots and one property that was proved by Wolfram is that alpha k is between this expression here and 2, so it is less than 2. The other thing that we can see is if we define the function here, and it is very important because it will help us to see the binary formula of the generalized Fibonacci sequence. So we can see that Fk alpha, the first real dominant root, it is between 1/2 and 3/4. So this was proved by Bravo, Gomez, and Luca. And they proved that the absolute value of Fk of alpha I, it is less than 1. And this will help us in the future to compute what we call the height of the element that we are going to use. Okay. The other thing that we can say is that in 2014, Dresden and Du, they proved that F and K can be written in this form. That is what we will call the binary formula of the generalized Fibonacci sequence. And the other thing very important and useful is that if we take Fnk, Fnk minus Fk alpha n minus 1, the absolute value is less than 1/2. And that will be also very useful in the proof. Now, the proof is done in many steps. The first step is to look at the lowest values, the smallest values. And for that, what we have done, we'll consider the values until k plus 1. So another way, if n is between 2 and or 1, it can be 1 or it can be 2. The 1 will be trivial, of course. If we consider n between 2 and k plus 1, we can see that Fnk, it is exactly a power of 2. So this can help us to solve very quickly the equation when we consider n between 2 and k plus 1. So in this case, because we are dealing with powers of product of Fermat's numbers, we can see that it cannot be a perfect power of 2. So there is no solution in this condition. Moreover, we can bound the parameters. So to do that, we consider these trivial inequalities, and we'll use the log, we combine that, and we come to the conclusion that n is between a plus b plus 3 and 1.71 times a plus b plus 542. And this will help us later when we are going to try to compare the parameters a, b, n, and to bound them. It will help us later. So here is the key lemma in the proof. So we consider any solution a, b, k, n of the initial Diophantine equation with a k greater or equal to 2 and n greater or equal to k plus 2. We have a deal already with n less or equal to k plus 1. We prove that the parameter n is less than the quantity. How we do that? We do that in 2 steps. So the idea to prove that is to use a very nice tool. And at this point, I can remind you that Michel had for so many years worked on linear form in logarithm. And the first tool that we use, it is a result on linear form in logarithm. In fact, if we consider any algebraic number, non-zero, eta, of a degree d over q. So we mean that eta is root of a polynomial of a degree d, and we can write the polynomial in this form, and then we can consider the height of eta defined by this formula here. So eta is always like that, and of course, because we are talking about Galois things, it is here we use a lot of result of a Galois or manipulation of a Galois group, because we need the embeddings, and we need that to obtain the height. Okay, so here is the main result that we use. It is a result, I will say, a variant of Matveev result obtained by Bugeaud, Mignot, and Sixek in the paper that I mentioned a few minutes ago. We can determine the height. Then we consider AJ with the expression greater or equal to this expression here. We consider B the maximum of the absolute value of the coefficient. And then we can prove that the form that we have is the absolute value is greater or equal to the exponential of the quantity. In fact, to obtain the height, we have to use the Galois group of the number field that we have here. So we will use the tool in the first part of the proof of the lemma. And what do? We take the equation from the beginning, we modify that twice. The first modification is to rewrite the equation in this form here. So rewriting like that, we can determine the upper bound, divide by expressions, and we obtain a form of gamma 1 with the form here. So the next step we do is we determine what is eta 1, eta 2, and eta 3, and we determine the height. After the height, we determine the lower bound, the upper bound of the form, and we combine that to obtain this expression here. So excuse me, I won't give all the details about that, but people who are familiar to the method of Baker's method will know that when you have a form like that, you determine the lower bound and the upper bound, you combine that and you obtain. Here, what is important is that we bound the parameter A. So we need to do the same thing for B. So what we do is we rewrite again the equation into this form, where we isolate here B. And also what we do is we divide the thing and we obtain the form we have here. The procedure is the same. We determine the lower bound, the upper bound, we combine that, and we determine a bound for the parameter B. So we have done for A, we have done for B. So this can help us to obtain a bound for N also, because we have seen the expression to bound N in terms of A and B. So we can have this bound here. When you look at this bound, it is very high. Already we have a 10 exponent 28. So a computer cannot handle that. The other thing we can notice is if we want to do that, we have to look at the lower case and the upper case of the parameter K. So that is the next step. And for that, we consider lower the values of K, and we use what we called here a reduction method due to de Vega. In fact, it is a method based on Baker-Davenport reduction, but there is another flavor here that we use in our method. So in fact, if we consider a linear form, we can bound the absolute value of the linear form in this form, and we can consider x between y and x0. Okay, x, it is in fact the maximum of the coefficient we have here, and x0, it is a positive integer or a positive number, if we can find the one. So from the linear form, we can divide by side 2. So we do that, and we have another form here, and we can use that here, the lemma obtained by de Vega. So we consider the distance to a real number, to an integer, whether it is the distance to an integer. And if we have this condition here, we can bound y. Okay. So this, it is very useful. It is a computational method. It does work when you don't have so many parameters. So that is why if you want to do a problem like that, you cannot consider so many factors or so many parameters. So we consider the linear form lambda 1, and lambda 1 is related to gamma 1. And so it is the first part of the previous lemma. And we were able to rewrite the absolute bound of the absolute value. And from the form we have here, we consider, and the bound we obtain here, we consider the parameters to apply the lemma. And we were able to see that the bound that we have very high, we can reduce that to 717. So that is the importance of the reduction method. So we did that for A. We can do the same thing for B. So we consider gamma 2, and we obtain a linear form related to gamma 2. We have done the same method, obtain a bound for the absolute value, and then consider the parameters. And we were able to prove that in this case, we have b less than 19. So at the end, we have, at the beginning, I didn't specify that. We consider A less or equal to B. So we have now A and B between 1 and 719. And this helps us to obtain the bound for n, because we know that n is bounded by the parameters A and B. So we obtain that. And at that level, a computer can handle that. So what we did after that, it is to run a program in Mathematica, and we consider the bound for A and B for n, and then we consider some condition we have seen a few minutes ago, and we obtain only the solution that in the main theorem. So the next, the last part is to handle when our parameter k is higher, and so we consider k greater than 360, and we have the condition in the key lemma, and we did some manipulation using the fact that Bravo, Gomez, and Luca, they prove that we have this condition here. We use that, we use also linear form in logarithm, and we came to the form that k is between, k is less than 10. But at the beginning, we proved the condition that k is greater than 360. So we have a contradiction, and this complete the proof of our main theorem. So that was the first theorem that we proved. Now, we thought about the other generalization sequences. Like we look, oh, by the way, before that, we look also some expression of 3 exponent a plus minus 1, 3 exponent b plus minus 1, and we use the same technique, the same method, and we use the generalization of the generalized Fibonacci sequence, and we obtain the same result. Now, we have other generalization, like, oh, by the way, for this problem, for this result here, I forgot that. We didn't use the same method like we have done using the Vegas reduction. We use here a reduction of Baker-Davenport, and another variant of that, it is the result obtained by Dugela and Petway, and that is what we use for the reduction. So we didn't use the Vegas reduction method. We use the flavor of Dugela Petway. Now, in the form we have seen, I will go back to that. I'm sorry. Yes, here it is possible that we will have a big quantity equal to 0. So if we have that, the method of Dugela-Petway cannot work. So we have to use another criterion called Legendre criterion, and we use this lemma here to obtain our result. So that is what I will say about the second result. As I said, we try to look other generalization, like we have a Luca sequence, and the generalized Luca sequence is the sequence defined by, of course, the same condition. We have zeros, and then we have 2 and 1, and we have the relation here that give us all the terms of the generalized, the k-generalized Lucas sequence. In fact, if we look the first terms, if k equal to 2, In fact, it corresponds to what we know as the Lucas sequence. We have a k equal to 3. We call that 3 Lucas sequence, and so on. Another that we can consider, because we discussed about a Pell sequence, we have also k-generalized Pell sequence. It is also defined the same way. We have the first term zeros. We have the P1 k equal to 1, and we have the sequence defined, the recurrent sequence here. If we look at the first terms, of course, for k equal to 2, we have the Pell sequence, and after that, we have the other sequence. So my question is, I asked quickly another question a few minutes ago. Can we do that for larger numbers of Fermat's numbers or other factors? It is possible, but it may be difficult. Can we obtain the same result with the generalized sequences that we have here? Yes, it is possible. We have some result, early result submitted, but it is early to give a result because it is under consideration. So it is possible. So we have a possibility to have a better result and more result using the same type of method. So this will finish my first part about my results, and the second part of the last part will be to talk about Michel. Okay, maybe it is early to talk about Michel because you have a special day for him tomorrow, but I won't be here tomorrow because I have a familial obligation. So I won't be here at the end of the conference to honor Michel, but I want to take a time to discuss about how I know Michel. Michel, I know him since 1992 when I was a student of Claude Lévesque. He's a good friend of Claude Lévesque, and Claude talked to me about him, his work, and I have read that. And he's a big reference for me. So for years, we built a very strong relationship. So we have traveled around Africa, and we have done so many wonderful things together. We try to help many countries. So we have been in Benin, my original country. We have been in Togo. We have been in Ivory Coast. So in one trip, we have covered so many ground. We have been in Benin, Togo, Ghana, Ivory Coast, and from there, everybody flew back to his country. We have been in Cape Verde. We have been in Congo. Besides that, for my conferences, we have met in Hungary. I remember one evening, Michel and I, we went back to Budapest, and we spent the night at the house of the Academy of Science of Hungary. And it was a very nice evening. We went together to eat, and we enjoyed time together. We have been in Turkey, France. I don't say Canada because we have met many times in Canada, and so on. So next year, we are planning to go to Benin again and Senegal. So I want to show a few pictures of the time we spent together. So here is Michel with Claude, my former advisor. So it is because of Claude I know Michel. And by the way, when I finished my PhD, Claude proposed me that Michel will be one of the members of my committee. but Michel declined that. I don't mind. He proposed a Mignot, and that helped me to know Mignot also and to work with Mignot. Michel and I, we have never had a paper together. It will come one day. I'm almost sure. But anyway, it is because of Claude that I met Michel. Here is also Claude and Michel when we were in Turkey. Michel, could you remember? No. Yes, we went to enjoy time. I think it was when we visited a place in what is where we have a journée arithmetic. Yes. So anyway, here is the two friends that we were together. Papaladi, Professor Papaladi. So, okay, here's our first trip in Benin. So we have a called Simpa in Benin. Here's the picture of the group. And we took a picture. We were about 8 to go together. So it was a very nice trip. We did enjoy. Here the bigger trip, the bigger team. In fact, here we don't have the former director of Simpa. So you can see myself here, Professor Papaladi, Professor Luca, Professor Claude Levesque, Adriana, and Jorge. So it was a very good group, and we were in Benin. Another picture of that. Oh, something we did nice. We planted the trees. They are growing. They are very well growing. So Michel is here. I didn't see him when he was planting his tree. So it was a very nice thing. Michel with Claude and a student of EMSP. Do you remember this picture? We were in Togo, close under a tree called baobab. It is in Africa. It is a bigger. It is a kind of a bigger tree, and they have a fruit. You can have a juice of that. It is very nice. So again, here another picture with people in Togo. Yes, I think here we were still in Togo. We have, I think we have a dinner with our host, the Italian ministers. Yes. Okay, here we are in Ghana, Cape Coast. The same thing here, Cape Coast, when we visited the slavery house. Yes. Now we are in Ivory Coast. By the way, let me tell you a story. We do like a friend, with like a brothers. Okay, we go, we buy. Anyone can buy, and at the end of the evening, we share everything we bought together, and we share. Oh, how much you spend? How much you spend? And we put everything together, and we share like a brother. So Michel is a very nice friend. So here with Tanoi. So it is still in Ivory Coast. Another picture here, when we went to Cape Verde. Yes, with our host in Cape Verde. The participants, some of the participants, when we organized the school there. So anyway, that is, oh, my last picture with, do you remember, Michel? It was in Turkey. We were in the boat going to, when we left, we were going to the second conference. So we took the picture in the boat. So that is all. I want to thank you all. Merci beaucoup.